There's your active chill beam. We talked a little bit about how we apply that. The biggest thing about active chill beams is the capacity. We're bumping that to 400 BTUs a square foot versus that radiant panel up there, which is about 40 BTUs a square foot. So you get 10 times the capacity out of an active chill beam as a typical radiant cooling panel. And here's some applications. Here's some beams that are up against an outside window. Now those are active, so they're actually blowing air at the window. Here we've got passive chill beams over the windows. Here's some where they're just in a row, and there's some just down the center of the room. Okay, this is interesting. We're seeing this now on a majority of jobs in the actual application of the chill beam technology. In a chill beam system, you still have a need for low temperature chill water for the DOAS and local units at the entrances for dehumidification. We also have a need for high temperature chill water for the chill beams, the radiant cooling panels, whatever else you might have that's going to use the high temperature water. So there's what you get, which is a 4-pipe chill water system. 2 pipes for low temperature and 2 pipes for high temperature. What we are noticing is that a lot of these jobs are going over the money because you get double the number of components in here, double the number of pipes. So let's go back to our old friend, the single pipe system, and we can make that look like that. This does a couple of things for you. We can get a very high split now. In this case, it's 16 degrees because the return water temperature to the chiller is the entering water temperature to the chill beams. Let's say it's 58. So this water, as it cascades, can return at that temperature right there. So in this particular case, the cascade is actually a help. It's not a hindrance because we can get this very high split, 16 degrees, as compared to what would have been 4 degrees. So we're going to reduce the number of pipes by 75% from 4 to 1, and we're going to reduce your flow by 75% because we can get a 16 to 20 degree delta T versus a 4 or 5 degree delta T over here. That's a big number. Yeah, huge energy savings and huge number of pipes. Again, we eliminate all the control valves, we eliminate all the balance valves. What we're suggesting here, if we have, as Jason was saying, multiple chill beams in a zone, say you had 5 or 6, pipe those reverse return. So now the entire system is self-balancing on the primary side and on the secondary side with the chill beams. What you'll discover in a chill beam system is you're going to have more devices to balance hydronically than you would have. As an example, in this room, if I had a fan coil unit, I'd have 1 balance valve. Instead, we have 1, 2, 3, 4, 5, 6. We got 9 chill beams. So that increases the balancing cost by a factor of 9. That's a big deal. Plus, you also have to balance the airflow. Now, you would have had to do that anyway, because those would have just been diffusers. So the air side balancing cost doesn't change, but the wet side does. So by piping those guys reverse return, using the load match system already, then hydronically the system is still self-balancing and we're not increasing the balancing costs. Okay, so what does this all do for you? Well, here's what it can do for you. Let's go back to a conventional all-air system. This is the electrical demand, blue again representing the generation equipment, and yellow is representing fan energy, and magenta is the pump energy. In a conventional chill beam system, we can reduce the fan energy but double the pump energy. With our concept, you can decrease the pump energy back to what it was before. So here, this is kind of interesting, instead of the distribution energy being roughly half, it's now only 20%. And I will submit to you, if you make that a ground source heat pump, like the Letteract folks have done at Penn Foundation, that is the most efficient system we can design in today's world. Nothing that's going to even come close to that.